Hi, welcome back to Calculus. Today we're going to continue our discussion of continuous functions. Specifically today we're going to focus on where a function is not continuous. Okay, now you've probably heard me say this word before, and if not, let me just go ahead and give it a definition. Where a function is not continuous is called a discontinuity, which I suppose that makes sense. I'm not sure I have that like written down anywhere specifically because I guess it's kind of intuitive, but here I'll write it down here. Where okay, I'll be a little mathematically formal. If f is not continuous at x equals c, then x equals c is called a discontinuity of f. Okay? Where a function's not continuous, we say it's discontinuous. And we refer to that value specifically as a discontinuity. Okay? So if for instance, if the function is not defined, well, at x equal 5, well, that's one way that a function fails to be continuous. We would say x equal 5 is a discontinuity. If there's like a vertical asymptote at 0, we would say 0 is a discontinuity of the function. Okay? So discontinuities come in two flavors. That's what definition 1.52 is about. They can be classified as removable or non-removable. Okay? Removable or non-removable. And basically there's a very easy way to figure out which one is which. A discontinuity at x equals c is removable if the limit as x approaches c exists. So if you're trying to figure out if a discontinuity is removable, then you need to show that the limit exists. And by the way, it's non-removable if the limit does not exist as x approaches c. Again, continuity and limits are inextricably linked. Okay, they're two sides of the same coin, limits and continuity. Okay, so a function is discontinuous, and that discontinuity is called removable if the limit exists. It's called non-removable if the limit does not exist. And I guess if you want to think about these in graphical terms, which is the point of this video, let's just take a look. In graphical terms, removable is going to be a hole in the graph. So that's very simple to look for graphically. If there's a hole in the graph at some x equals c, then that's going to be a removable discontinuity. Because if there's just a hole there, the limit is going to exist. Now, there's a few different ways that you could have a non-removable discontinuity. Okay, a non-removable discontinuity, you could have a vertical asymptote. Because the limit does not exist when you have a vertical asymptote. Or a break, or a jump, a gap. These are all the same thing, but different people call them different things. A jump, a gap. I probably refer to it as a break or a gap in the graph. Because if there's like a break in the graph, again, that'll make sure that the limit does not exist. Again, fits with our definition. Okay, so let us look at this function. Here we are, y equals f of x. First thing I notice is that, hey, we're looking at a graph. Second thing I notice is this is definitely a piecewise graph. Like this portion right here is like some either two linear, it's just two linear functions put together. I was about to say it might be absolute value, but it's not symmetric for absolute value. So that's just two linear functions put together. And here's another linear portion over here. And right here, this part where there's an asymptote, that's like some version of the reciprocal squared function. It's actually the reciprocal squared upside down, translated 3 units to the right, and then some number of units up. Maybe 6 units up, and it looks like it's been scaled as well. My point is this. Like, this is definitely a piecewise function. It would be like f of x equals, it would be like it's a big brace. Or we can look at that. Like that first function, what is it's a y-intercept of 3 and a slope of 1. You would say the first row of the piecewise function would be what? It would be negative x plus 3. And we would say that's for, well, it's the arrow indicates forever to the left. So we would say that's what, x is less than 1. That'd be the first row of the piecewise function. The second row of the piecewise function, what's this? The equation of this section. Well, it looks to me like that's, what is a slope of 2? If you extend it, it would go through the origin. So the equation of that line would be what? 0 plus 2x, or 2x plus 0, or otherwise known as 2x. But that's only valid between 1 and 2. But we would say negative 1 strictly greater than x less than or equal to positive 2 because there's a solid dot there and an open dot there. Anyway, my point is you could keep doing this, and there would be another rule for this function, and there would be I guess 4 more. So there would be not 4 more, 4 in total rules. Okay, this would be what for x is between negative 2 and 2, and this last one would be actually no, there would be 5 because there's this dot we'd have to define differently. Anyway, it's a piecewise function. Now, why am I even bringing this up? Why am I bringing up the fact that it's a piecewise function? It doesn't really matter what it is because we're going to rely on the graph. We're not going to rely on that algebraic definition. Why do I bring it up? Say this: f is piecewise. Hence, theorem 1.5.2 does not apply. What did theorem 1.5.2 say? Theorem 1.52 said that for our typical functions, polynomials, rationals, radicals, exponentials, trig, logarithmic, they are continuous on their domain. Well, if theorem 1.52 does not apply, well, then this function is not continuous on its domain. And why is it important I say that? Because the domain of this function is not going to match where it's continuous, and we'll talk about that once we're finished. In fact, let's do domain first. Let's do the algebraic domain question. It's not asked here specifically, but let's just note it. So let's say note the domain of f is, okay, so this would be like a question I would give my college algebra students. What's the domain of that function? Basically, where is the function defined? Where it's not going to be defined is going to be where there's a hole and not a solid dot, and where there's a vertical asymptote. So notice there's a hole right there with no solid dot above or below. So that's not in the domain. So 1 is not in the domain. Also notice that arrow indicates we go forever to the left. So it's going to be negative infinity to 1 union 1 to something. Now, where's the next problem with domain? Well, notice here is not a problem with domain. There is a hole, but there's a solid dot right below it, which means the function's still defined at 2. The y value, f of 2, is 4. Okay? But now there's a vertical asymptote at 3. So we would say 3 is not in the domain because, of course, a function is not defined at a vertical asymptote. Union 3 to what? Okay, here's something weird going on. But just like at 2, there's a hole there, but there's a dot, a solid dot right below it, which means the function is defined there. And then so you keep looking to the right, but notice, okay, that pattern just goes on forever to the right. So here is the domain of the function. Now let's look at where it's continuous. So I guess I'll just write this. F is continuous on, okay, and let's see what happens there. But let's first look at the discontinuity. So consider the graph below. We want to figure out where it's continuous, the intervals, but we want to list and classify the discontinuities. So let's look at two columns here. Discontinuities. First column, and then let's say type, I guess, on the second column. Removable versus non-removable. So let's just work from left to right. So the first one we see is at 1. There's a hole there. So the question is, and by the way, our definition of discontinuity is this, like a test. The test for continuity, this was a box a little while ago, was a three-pronged test. F of C is defined. The limit is x approaches C of f of x exists. And the third thing is that limit as x approaches C of f of x must equal f of C. If any one of those three is not true, then the function's discontinuous. So my first discontinuity working left to right is 1. Why? Because the first bullet point is violated. The function's not defined at x equal 1. So x equal 1 is a discontinuity. Okay, now what type is it? Now remember, the type is dependent on whether the limit exists or not. It's removable if the limit exists. It's non-removable if the limit does not exist. So the question is, does the limit as x approaches 1 of f of x exist? Well, I think this is pretty easy to see, right? It's from the left, the y values are approaching 2. From the right, the y values are approaching 2. So yeah, the limit is 2. So since the limit exists, we don't care what the actual number, the value of the limit is, we just care that it exists. So that means this is going to be a removable discontinuity. A removable discontinuity. Okay? Where's our next problem? Our next problem is at 2, because there's a gap there. So what's the issue there? So the function is defined. That solid dot right there means the function's defined. So that's not the problem. The first bullet point in our test for continuity is not the problem. The second one is. Actually, if the second one, actually, I should say, if either of the first two are not true, then the third one's automatically not true. So for the last example, I should have said this: f of c is not defined, which by default means that can't be true either. So I should have been more specific there. Okay, so if either the first two bullet point fails, then the third bullet point must fail. But I guess the alternative is the third bullet point could fail by itself, and we'll see that in a few minutes. So for x equal 2, the limit does not exist. Why? Because if you look at the limit as x approaches 2, the limit from the left is 4. The limit from the right up here is 5. So the left and right hand limits do not match. Again, I'll say that specifically. The limit as x approaches 2 from the left is 4. But the limit as x approaches 2 from the right of f of x is up here at 5. So the regular two-sided limit as x approaches 2 from both sides does not exist. Okay, so that tells me what? That tells me that it's a non-removable discontinuity. Non-removable. And again, that's kind of what I set up here. That a non-removable discontinuity is going to be a break or a jump. I would call that a break in the graph or a gap in the graph. Okay. All right. What about the next error-ish, or where the next discontinuity? Now, obviously, the function has an issue at 3. So x equals 3 is a discontinuity. There's a vertical asymptote there. Okay. Okay, so what can we say about the vertical asymptote? So we need to see, does the limit exist or not? Okay, so what is the limit as x approaches 3 of f of x? Okay, so from the left, we see what's true. That function's going off towards negative infinity. From the right, what do we see? That function's going off towards negative infinity. So that since the behavior from the left and the right are the same, we know that the limit is negative infinity. Now, here's where we gotta be careful. Remember, this is a special form of D in E. Remember, if we say a limit equals negative infinity or positive infinity, that's just a special notation that says the limit does not exist in this case because there is unbounded behavior toward negative infinity. It's a special form of does not exist. So if the limit does not exist at x equals 3 and x equals 3 is a discontinuity, then that means we have a non-removable discontinuity. By the way, which what I set up here, a non-removable discontinuity will be a vertical asymptote or a break in the graph. Okay, last example here, what we said 4 was weirdness was happening here at 4. Notice there is a hole in the graph. Okay, so that the function is defined at x equals 4, but there's some weirdness going on. So x equals 4 is a discontinuity. Now, why is it a discontinuity? Let's think about this. Let's go to our 3-point test. Okay, f is defined, yeah. There's a solid dot there, so the first bullet point is not the trouble. Does the limit exist? Well, yeah, from the left, the limit is what, 5? And from the right, the limit is 5. So that's not the trouble. So we would say the limit as x approaches 4 of f of x equals 5 from both sides. So the overall two-sided limit is also 5. So that's not a problem. Check mark. That's not a problem. Check mark. But what do we see? F of 4 equals 3. These two things are not equal. That's the trouble, which is bullet point number 3 in our test for continuity. This is the one that's violated. So the limit exists, it's equal to 5. The y value exists, it's equal to 3, but they're not equal to each other. For the limit to be continuous at that value, at 4, the y value has to equal the value of the limit. And here the y value is 3, the limit is 5, therefore the function is discontinuous at x equals 4. Now, but here's the thing, the limit exists. So since the limit exists, we know that it's a removable discontinuity because a function has a removable discontinuity if at that discontinuity the limit exists. And here the limit does exist, it's 5. Okay? So basically, it's when you have a hole, those are your removable discontinuities. And so it's like we could, if we wanted to, we could redefine this piecewise function and put that dot right there and erase that dot, and then we would have a continuous function at x equals 4. And then at x equals 1, we also said that was removable, And so if we wanted to, we could redefine that function such that it simply has a dot there so that it is defined. Okay, so that's what it means to be removable. You can remove the discontinuity by a simple redefinition of the function. So those are called removable discontinuities at 1 and 4. However, you can't do that at 2 and 3. When you have a vertical asymptote, there's no way to fix that with a single point. Likewise, at 2, there's no way to fix this with a single point. You can't bridge the gap with a single dot. We fixed this situation with a single dot. We fixed this situation with a single dot. We can't fix the situation at 2 and 3 with a single dot. Therefore, they are non-removable discontinuities. But let's go back to the original. There's the original. Okay. By the way, where we've identified where the function is discontinuous. So where is it continuous? I started the sentence up here. F is continuous on, well, let's see, everywhere where it's not discontinuous. So everywhere except for these values, which would be negative infinity to 1, union 1 to 2, union 2 to 3, union 3 to 4, union 4 to infinity. Everywhere except for the discontinuities. So again, I want to drive the point home here that theorem 1.5.2 does not apply because this is a piecewise function. And we can see here explicitly that these two things are not equal. Theorem 1.52 guarantees they'll be equal if you have a specific type of function. But we don't have that specific type of function here. So that's why those two things are not equal. The domain, the intervals in which the function is defined, is not equal to the intervals in which the function is continuous. Okay, so there we are. Removable discontinuities versus non-removable from a graphical perspective. So in the next video, we'll talk about a little more about vertical asymptotes and identifying removable versus non-removable discontinuities when you don't have a graph to look at. So how do you do all this business algebraically, analytically, when you don't have a graph? Okay, but that'll have to wait till the next video. As always, let me know if you need help. Always more than happy to help you. And in the meantime, make sure you're working that two plus hours a day. That's the key to success in this class, is working hard every day, keeping your head in the game every day, focused on calculus. And if you do that, you'll be fine. All right, I'll see you in the next video.